Hi there, my name is Tanner and I'm doing the final design review presentation for Wingstop. So I'm the team lead here, and then we have Chase Wilson in charge of CAD and graphics, Marcus Cloven in charge of weights and structures, Emily Dunn as the configurator lead, Tyler Van Duet in charge of aerodynamics and control, Kyle Shepard as the system avionics and ground support lead, Sarah Beth Evans as the capture manager, Anthony Corpez in charge of propulsion and power, and Weston Gorham in charge of systems, avionics, and ground support. So here's the contents of our report. Initially, I'm going to do a recap of our CDR, going over our objectives, mission, and market analysis. In the part 2, we're going to look at the SQ-121, some of its general specifications, and the final rendering for the plane. And in part 3, I'm going to analyze the design specs, propulsion, aerodynamics, weight and structures, and controls. So recapping CDR, our objectives and mission analysis are listed here. Some of our big ones are it needs to be able to break the sound barrier, have a range of 60 miles, weigh less than 55 pounds at gross takeoff weight, and utilize a commercial off-the-shelf gas turbine. Here's our market analysis. Currently, the SUAS market doesn't really exist. Project Boom and Kelly Aerospace are currently designing concepts, but they are only concepts, and there is no aircraft on the market that currently fits that supersonic UAS category. So off to my side here, you can see our concept design for the SQ-121. Some of its specs are a total length of 47.4 inches, a wing area of 468 inches, and a wingspan of 40 inches, giving it an AR of 3.42. Its GTOW is 54.5 pounds, and it has a max subsonic thrust of 88.2 pounds and a max supersonic thrust of 200 pounds. Its approximate C sub L is 1.5, and its CD naught is 0.0265. Some other general specifications: it has a top speed of 1.2 Mach, and it cruises at 5,000 feet to accommodate for its fairly small fuel tank. So if we have it fly too high, it's going to run out of fuel before it's able to reach the range we need. And it has a jet thrust of 76 pounds at 5,000 feet. So the chosen motor for our SUAS was the AMT Titan. It's a gas turbine that weighs 11.5 pounds fully equipped. At sea level, it has a max thrust of 88.2 pound force, and it has a max consumption of 36 ounces a minute and a specific fuel consumption of 1.53 pounds per pound hour. The rocket motors to help propel our aircraft to Mach 1.2 are J135Ws. Each one weighs 2.5 pounds and provides 61.6 pounds of thrust, or peak thrust, and has an average thrust of 35.3 pounds for a total burn time of 7 seconds. Here's our avionics and systems analysis. Our system overview: we have external environmental sensors, positional sensors, control surface actuators, transmitters and receivers, a computer, control UI, and batteries. And then our general configuration is our electronic system, which is controlled with an Arduino microcontroller setup, and it sends and receives data via transmitters. And our computer UI is connected to a long-range transmitter, which passes signals to a quadcopter, which passes the signals from there through a high-strength transmitter to the supersonic UAS. For takeoff, we're going to use a rocket sled, like you can see here to the right. The aircraft has to be able to take off from a 25 by 25 foot space, so this system would allow for this. For landing, we're just going to use a low-speed grass landing. As we prepare for takeoff, for landing, we're just going to lower our speed as much as possible and let it land on a soft patch grass. So our SQ-121 is based off of the design of an SR-71, so you can probably tell. We chose our AMT turbine because it is the most likely to accommodate our propulsion options. It has a relatively low weight with a high thrust output, and our rocket and SR-71 with the turbine is a good setup to meet our COTS jet engine constraints, and our dual rockets are placed in the area under the horizontal stabilizers and were necessary as the jet turbine does not make enough thrust and it also stalls out at Mach 0.8. The placement of the rockets is placed closer to the fuselage than on an SR-71 because solid propulsion rockets do not make a constant thrust output between units. So the further apart they are, the more moment they can cause. So we want to get those close as possible to minimize that effect. So looking at our propulsion analysis, as I mentioned earlier, the Titan alone produces 88.2 pounds of thrust, but at our cruise altitude of 5,000 feet, only 76 pounds of thrust is produced. But in order to reach the supersonic design for UAS, we need about 180 pound force of thrust based on our drag puller here to meet our goals. So in order to do this, we needed to pick 2 model rocket motors in order to meet that criteria. So as you can see here in our new graph on the right, our thrust available has increased a lot to 200 pounds, and that is due to our 2 rockets located, one on the left and one on the right, and these produce a significant amount of thrust for about 7 seconds. For our aerodynamic analysis, our team selected a delta wing configuration for our planform. We chose a delta wing because they have an attached shockwave which generates lift, has high structural integrity, and a low aspect ratio which maintains the surface area. Looking at our airfoil analysis, we chose thin airfoils, which are almost required for this supersonic vehicle to minimize the drag forces at high velocities. We chose the NACA 64206, the red and brown lines, because of their desirable characteristics at high Mach numbers. At cruise altitude, our aircraft would be aiming to reach Mach 1.2. An estimation of the total drag on the airframe at this velocity would be about 95 pounds force, as you can see here on the graph to the right. So breaking down their weight, with the jet turbine weighing 11.5 pounds, our rockets weighing 5.2, us having about 19 pounds of fuel, the fuselage weighing about 10 pounds, having roughly 4 pounds of avionics and systems, and a 5-pound payload with cameras, we're looking at a total weight around 55 pounds. So here's some pictures from our aircraft. Here's a close-up of the nose of our aircraft. Right here you can see a glass or a transparent window with our FLIR camera, and then behind here are going to be our antennae to send and receive radio signals from our quadcopter antenna. I didn't touch on that earlier, but the reason we need a quadcopter is because antennae transmit and receive better at higher altitudes. So having an antenna low to the ground, like a ground station, is not going to be able to transmit as far as a high up one would be. So putting the transmitters and receivers on a tethered quadcopter would be able to cast a lot farther for those 26-mile radius needed to reach up to this aircraft. We also have our little window here for our FOV camera. Here at the back, we have a air intake warning and then a hot exhaust warning for the tail of the aircraft where the engine is. Here is a side view of our aircraft. We have our turbine right here. This is a servo motor. These weren't really placed correctly. In reality, they'll be over here, up at the front with our FLIR camera and FOV camera. Here's our fuel tank. And then extra room here will be to let air flow in. This is our air intake. And then here's a rear view. You can see our turbine, and then this is where our rockets are. And then this here is a video rendering of our aircraft. you can see that we tried to put some tapering in. Our computer modeling software had a little bit of an issue whenever we did that, but we put some tapering in, and we've area ruled the fuselage along the wingspan as it got wider in order to help with our drag. And we also added strakes here to help with drag as well. So here's some of our sources we used for this report. And we want to say a quick thank you for having an opportunity to learn about how to design aircraft in this class, and for listening to our presentation. And you can count on the SQ-121 spying on a country near you. Take care.